My name is Satish Chandra. I'm going to talk about machine learning for developer productivity. A little bit about myself. I'm a software engineer at Google. Before this, I was at Meta for about 5 years, and I led efforts to build and deploy several machine learning for software engineering tools while there. I am here to share my enthusiasm for this area. I also want to note that all opinions are my own. Okay, so let's get started. Here's what we are going to do today. I'm going to provide a very gentle introduction to this field. I'm going to illustrate the ideas using code completion and code recommendation, and I'm going to sprinkle around some pointers to further readings that you might find useful. Some disclaimers. So this tutorial is really aimed at people who have no background in this topic. You will not be able to run off right after this talk and train some models, but you will know where to look for more information. And my viewpoint as expressed in this talk is biased by my own experiences. Okay, so when we talk about machine learning based tools, perhaps the most prominent one that comes to mind is a modern autocomplete. And here what you are seeing is Visual Studio. It is completing not just the next token, but the entire line, as you can see here. So this is pretty cool. And now let's see Copilot in action. So here I write the name of a function, I write a docstring, find the lowest common ancestor of nodes A and B for a tree rooted at root. And once I finish typing, we'll see Copilot do its magic, and here is that magic. So that's also pretty cool. Let's look at something slightly different. So here we are seeing Google Sheets, a spreadsheet thing where as you hover over certain cells, it actually suggests what formula you might need in that cell, and you just have to hit tab and accept it, and that becomes your formula. So this is kind of autocomplete for formulae. Okay, let's look at one more thing. So here is AlphaCode. AlphaCode is a tool created by DeepMind. And on the right side of the screen, you will see a description of a programming competition problem. And this description actually goes on for multiple pages. It will have some tests included in it and so on. So it's really for human participants to read and understand what the problem is and then go off write their code. And for this particular input, AlphaCode will go off and generate this code for you. So that's also pretty cool. They say on their website is that AlphaCode would rank about median in terms of ranking of programmer participants. So that's nice. Okay. And all of this has kind of begun to catch attention of media. So here I'm showing you photo of a page from the Economist magazine, and they write, the article title is AI is transforming the coding of computer programs, and the byline says the software engineers of the future will themselves be software. So think about it, whether you agree with that or not. All right. So let's get into what makes these kinds of tools possible. Just a little glimpse of some properties of code that makes some of this possible. So the first property is, as I will describe, is called naturalness. Now in English language, if I say I'm going to go to Starbucks to grab some, well, you'll say what comes after some is coffee. That you know from your everyday experience. You can predict what words come in English language after the speaker has spoken about halfway. Now let's see in the context of computer code. So on the left, if I show you this fragment of code for I equals 0, I less than 10, and the cursor is over there, it would be a pretty good guess to say I++, close paren and curly brace open. And you know this because you have seen lots of code like this, and you have pretty good high confidence guess that this would come next. Similar to how you do this for natural languages. On the right hand side, you see loss dot, and if you are a PyTorch user, you would probably guess, yeah, it's backwards. So this property that code is predictable based on what tokens we have seen just now, that property is called naturalness of code. It's analogous to what we experience in natural languages. That's why it's called naturalness. And this paper mentioned here talks a lot more about it. Okay. Another property, bimodality of code. So code is, of course, meant to be executed on CPUs, but code is also a medium amongst programmers. So people write code so that other people can read and understand it. And they use conventions and names in code that is often self-explanatory. So here, let's say you have a question, how do I get a platform dependent new line character? And let's pretend that this fragment of code is in fact a pretty good answer to that question. It is in fact possible to retrieve this particular code snippet from, say, millions of code snippets out there, just on the basis of the words that are contained in the identifiers and strings in this code. So people have used this kind of property for, say, code search. Let's look at something else. So if you look at the box on the left, x dot weight times x dot height plus y dot weight times y, and we are trying to get the computer to predict what comes after y dot, the second y dot, where there is question marks. And it would be a pretty good guess to say it's y dot height. Maybe type wise it could have been y dot weight, but in this particular context you pretty much know it should be y dot height. Let's look at the other text box, the one on the right. Here we are talking in the context of, let's say, a board game program where there is a function called mark point, and it usually accepts arguments called x and y. And let's say that's what you usually find, but in one particular occurrence, you see y comma x. Well, it would not be unreasonable to mark that as a possible bug, and indeed that's the idea that this paper mentioned at the bottom went after. Here is a copy paste error. So here someone defined a variable called class, a certain non-null class, and then they defined a variable called first, but they copy pasted, and so that thing highlighted there is a bug. And indeed we did find a subsequent GitHub pull request that was actually fixing that bug. And how to find and flag these kinds of copy paste errors is mentioned in this paper cited here at the bottom of this page. So we have seen some properties of code that machine learning models leverage in order to make interesting predictions that are useful for developers. But as with anything ML, we have to ask, where does the data come from? And that data in this case is essentially large number of, say, GitHub repos, also not just code snapshots, but also version history, commit logs, other metadata, and so on. We have a lot of coding information implicit in forums such as Stack Overflow. And then inside companies also there is lots of code and issue tracking and test history and internal discussions and so on. So all of these are really data that machine learning can crunch and produce interesting information for use by developers. Along with all that data, there have been, of course, lots of advances in machine learning itself. Just until a few years ago, recurrent neural networks were the thing, LSTM and all that. And then from about 2017 onwards, transformers took over the world. And you hear about GPT and BERT and all of that. Today, transformer models have billions of parameters. But there are other kinds of neural networks that are used as well. For example, graph neural networks that are quite useful to represent programs. And then leaving aside just the neural networks or deep learning, there are also techniques from information retrieval and data mining that come in handy from time to time. Okay, so what do we do with all this data and all this ML? Well, you can build a variety of tools. Some of them are mentioned here: code search, autocomplete, code recommendation, bug finding, bug fixing, all of that. Here I'm showing on the right a couple of screenshots from blog posts that have appeared in recent past. So this is a pretty active area. These tools are beginning to get real. But beyond just these very coding oriented tools, I would say that machine learning has the potential of being used in other parts of the software lifecycle. So, for example, code review, issues that come up in continuous integration, or even farther out in production, troubleshooting, and so on. And in fact, there are works out there that talk about many of these issues. So, it's a pretty exciting field. Now, what we are going to do is to look into a little bit of detail in autocomplete. I want you to get a high-level idea of how this autocomplete might be implemented using machine learning models. Okay, so autocomplete really needs no introduction as such. If you look at this middle picture on this screen, you might recognize this. You're writing some code, you say string dot, and then pops up a menu that shows all kinds of completions that are possible after string. And perhaps you wanted that A to I, but it is kind of the sixth thing from the top. And so autocomplete is great because it saves you the effort of typing the next tokens, but it's also a code discovery mechanism because you might not remember all of these possible API names all at once off the top of your head. But once this menu pops up, you might get reminded. So that's pretty cool. So this autocomplete I would say, of previous generation was essentially type-based, where it would give you maybe an alphabetically sorted list of all the possible completions that might come after something. Obviously, this is sometimes clunky to use if there are lots of choices. And sometimes people have done things like using simple statistics to rank this list. Yeah, and ideally what you want is the intended or the most likely completion to really be right at the top. So you could just hit tab and off you go. And indeed, that is what is possible by modern day ML-based autocomplete. So to understand what happens there, I have to tell you a little bit about the technology behind it. And we are going to talk about language models. So language models are gadgets that predict what comes next in a stream of tokens. So here, for example, if someone gives this sequence of k words, I'm interested in what comes next given this these k words. The what comes next is denoted by those question marks. So a language model will tell me that, hey, the probability of token I given this context of k words is, let's say, 0.85. Probability of token j given that same context is much smaller, maybe just 0.01, and there will be probability of several other tokens mentioned here. And if you are building an autocomplete, you would probably want to suggest the highest probability token as what is likely to come next. So the question is that how do we learn these language models that we can then use in autocomplete? And that is where the magic of neural networks comes in handy. There are other ways of doing things also, namely n-grams, but here let's talk about neural networks. So this slide has a lot of content, but let's first look at the bottom line that says map, open parent, string, and dot. And now look at the very top where it says open parent, string, dot, and a to I. And the purpose here is that, let's say if at a certain point in time, say time t, if I have seen, say, map and open parent, then I want this gadget called recurrent neural network to tell me that given this information or the context of map and open parent, the likely thing that comes next is string. And if I was given map and open parent string, then it should be able to say that the most likely next thing is dot. So this is a neural network called recurrent neural networks. And let's just get a little bit of intuition. How does it learn to make those predictions? So first, the tokens like map and open parent string, they get converted into a numerical representation, typically a vector of numbers. That vector could be, say, 128 entries or 256 entries. And this numerical representation makes it through the gadget. And what comes out essentially is equivalent of this probability table that says that, well, given whatever we have seen in terms of numerical representation of tokens so far, what comes next is as follows. The probability that open parent comes next is 0.5. The probability that equal sign comes next is 0.1, and so on. And from this, you can read off what is the highest probability token and say that, okay, that's what I'm going to predict comes next. Now, the learning part, because we want to talk about how does it learn, is, let's say initially it actually gives some kind of a random ordering. Maybe the highest probability thing shows up as something other than the open parent. So you look, so now, because during training we know that open parent is the right answer in this case, we are going to create a signal saying that, hey, I wanted the probability of the open parent to be highest in this particular context. And that signal kind of travels backwards through this machine, and it trains the parameters of this machine to try to make it so. And the parameters are essentially matrices here, denoted by those bold W things mentioned on the page, WHH, and so on. So there is the learning part that sets these matrices, and then there is the prediction part that uses the values encoded in those matrices to compute these probability tables. So that's about as much as I can tell you in the available time. There is lots and lots of information to read out there about this construct. But what I want you to realize is that essentially what just happened here is a neural network learned a language model, and then this language model can be used for autocomplete applications. So hopefully this gives you some intuition of how things work. Okay, so now this is a pretty simple case, but still, if you look at this code context as shown on this page, and let's say our cursor is after sys dot, and we are expecting argv as the right answer. Such an recurrent neural networks, as shown in the previous page, if trained reasonably well, should show you this right answer at the first rank, which is what we want. And in this particular case, we tried a couple of other prediction mechanisms, in one case, a tree-based solution, and all of them were able to predict argv as the top-ranked suggestion. So that's pretty good, but contexts differ. So here is a different context where we are after IP equal sign, and let's say we expect the word socket to be predicted. In this particular case, maybe our RNN ranks the prediction of socket actually pretty low, and maybe some of these other solutions also rank the right answer lower, or at least lower than rank 1. But there are advances in this field. So it turns out that if you use transformers, in this particular example, the rank of the right answer is in fact 1. And this is, of course, one example, but this paper mentioned here on this page shows that across a pretty large evaluation set, we can see that the rank of right answers computed by transformers is uniformly better than some of these other solutions. So with transformers, this kind of autocomplete actually works pretty well. We didn't really we don't have really time to get into the innards of transformers, but suffice it to say here that transformers are essentially very powerful language model learners. They were built for natural language processing, but it turns out that they are pretty effective for processing code as well. The paper mentioned here actually is the transformer paper, so it's worth looking at. And there are lots of blog posts out there that talk about how transformers work. So that's all I'm going to say about transformers. I do want to say that this mechanism, this RNN type mechanism that I showed you for next token prediction, that's a pretty basic mechanism. More sophisticated architectures do exist. So here, for example, we use a what is called encoder decoder transformer architecture, where the encoder takes the code before the cursor and perhaps code after the cursor as well, if there is any, creates a representation of that code and passes it on to the decoder that computes either one token or perhaps a sequence of tokens up to the end of the line, or perhaps even multiple lines after the cursor. And this was the subject of the blog post that I mentioned before from Google. Okay, so this was autocomplete, but neural networks have been used for other kinds of software analyses. We put together this article in the communications of the ACM magazine earlier this year. You might want to look at it. I want to just mention a few ideas from here. So in most of these applications of neural networks for software analysis, the high-level design gadget is often the following: that we input code tokens converted into numerical vectors. This is the embeddings that is mentioned on the left side of this page. And you end up with a summary representation of that code fragment, which is also a numerical representation. And then how a neural network is used to create this summary representation, there are lots of choices. So for example, you may be using a feed-forward network where you just simply input the token embeddings as a concatenation of them, and out comes a numerical representation. Or you could input the token embeddings as a sequence, like we did in RNNs, or is like how it is also done in transformers. Or you could have tree structured models or graph structured models and so forth. So you can preserve a little bit more information about the code if you wanted to, rather than just simply looking at code like only text. So if you wanted to use the tree structure, you could, and so on. So, okay, so what we get in the end is this summary, which is a numerical representation of that code fragment. And then what you do downstream from that is to create something which could be, say, let's say you are trying to build an application that says whether a code fragment has a certain kind of bug or not. So that's a binary classifier. Or you might be interested in asking the question, given this context, what is the most likely type of a certain identifier? And it might give you an n-ary classification saying that here are the probabilities of various types. Or you can use it for sequence prediction, as in autocomplete, like we saw earlier. So these are some of the possibilities that you can explore, and there are, and the paper actually shows examples of each of those. Okay, the modern way, or the current way rather, of doing things would probably be this design called pre-training and fine-tuning. This is in the era of large language models. And here the idea is that perhaps for the particular application that you have in mind, you don't have a lot of so-called supervision data or label data, but maybe you have lots of code out there in general anyway. So you could use something called a pre-training, that uses what is called self-supervision to sort of partly initialize a neural network. And this part doesn't need any label data, but then you use your little bit of label data that you have at hand to further uh, specialize that partly baked neural network with what is called fine tuning, and prepares it for carrying out predictions. So this model is used quite often these days. And a very good example of this architecture is the neural network model was presented by Devlin and others, and this picture is from that paper in 2019 called BERT, and then subsequently people adapted BERT for representing code in this paper called CodeBERT. So today, even if the transformer models are different, the general design idea of pre-training and fine-tuning is quite popular. Okay, so that was about neural networks and how neural networks are used for code-related prediction tasks. I want to switch gears a little bit and talk about a non-neural technique. And this part of the talk is based on the paper mentioned here. It's a code recommendation technique. Okay, so I have to tell you what is code recommendation. So let's say there is an Android engineer and they are working with Android API, and they write down this line of code. This particular bitmap factory dot decode stream is from the Android APIs. And if this is a novice programmer, they might wonder, well, is that it? What if, can I get feedback from some expert programmer who might tell me a thing or two about what else I might need to do here? So I'm going to now show you a small recorded video of a tool that essentially serves as that expert programmer to give advice to our notice. So when I play this, you will see that those two lines of code written in this buffer will be selected, and on the right hand side the tool will show a series of code recommendations. It will move fast, so you won't have time to read that, but after the video you will see the actual recommendations in slides to follow. So let's play this video for just a moment. We selected this, and what you're going to see is recommendation 1 and recommendation 2 and recommendation 3 and so on. So it shows 5 recommendations, each of which is a code fragment that gives a specific kind of information to the developer as to what code could come around the kind of code that they have written on the left hand side. Okay, so what are these recommendations? So the first one shows that, and the additional lines are shown in this kind of slightly slight blue background. The original lines that the developer wrote is shown in bold. So here the recommendation is that maybe some people also set some options. So this options might be useful, for example, to reduce memory usage. And this information is gleaned from seeing 5 different methods that occurred somewhere in the wild, looking at, say, millions of methods or whatever. But that's what the tool found for you. A second recommendation is reminding you to maybe you should close your input stream. And this information was gleaned from, say, 6 different methods. And here is a third recommendation. It is reminding you that, oh, there might be an exception, and at least some people thought that they should be catching this exception. And that information was gleaned from 4 different methods. So in each of these cases, some useful information around the code that you started with is being offered to you. And it's up to you if you think that's useful. Okay, so here is a problem statement. We have at our disposal a very large corpus of code, say millions of methods, and we have a query code snippet, by which mean that we have just written some code. We are going to use that code as a query. And the goal now is to find code that is similar to the query, and we want to show some extensions to the code that we just wrote or the query that we have in hand, but we don't want to show all occurrences of extra code. We want to distill down to some representative extension so that the information is consumable for the developer. So this problem is the code recommendations problem. Okay, so the way it works is in 3 steps. First, we carry out a feature-based search, and then we cluster and intersect. And I'm not going to talk a lot about clustering and intersecting, but let's look at feature-based search. So first thing we do is to, given a code fragment, we are going to create a what is called a one-hot feature vector. And this is just a large vector where each feature is either there or not there, and shown by binary values. And we are going to assemble such a vector carefully ourselves. Now, in contrast, neural techniques often create embeddings, and those are computed based on the neural network itself, and we often don't have a lot of control of what is represented in those embeddings. But here we are using a non-neural technique, and we are composing these feature vectors ourselves pretty carefully. Okay, so we start with a parse tree of this code fragment, and we are going to first look at all the leaves, and these make features, except that local variables could be very specific to specific occurrences. Different methods that are even similar enough might use different names. So we are going to kind of blur out names of local variables and just use like a hash sign var as our feature for a local variable. But all the global names of types and methods will be retained as explicit features, and those are the features you are seeing in the list on the left. And notice that this literal value 0 is also included as a feature. So these are kind of our token features that occur at the leaves of this parse tree. And then we will try to capture a little bit of structural information, not the full parse tree, but a little bit of structural information about the tree. So we look at where the token view was hanging, and we look up at, say, in this case, 3 levels of ancestors, and we capture what was the syntactic node type of each of those ancestors, and we record that whether this leaf view was to the left child of that interior node type or to the right child. So that information is shown in these 3 features shown on the bullet list on the left of this page. And then we can capture a little bit more information about the relationships of these leaf nodes to global names. So here we captured the information that in a left to right sense, view group precedes this var, a var, and that get child comes after. So it captures a little bit of that relative positioning of these 2 things, and so on. So we also capture whether 2 occurrences of some, how parent node of multiple occurrences of the same local variables might be related. So that information is captured in the form shown here. So actual meaning of all of these features is perhaps not important. You can look at the paper, but the idea is that we are doing a very handcrafted featureization of this tree and composing our feature vector carefully. Okay, so once we are done doing all of that, let's say this is our feature vector, lots and lots of features computed here and represented as a one-hot vector. So we have that from our code snippet. Now, what we are going to do is we are going to pre-compute these kinds of feature vectors for all the millions of methods that we know of and store these feature vectors in a database. And when a query comes along, we are also going to featureize it with the same kind of featureization. And then we are going to use a very fast lookup mechanism that tells us, okay, from this database, which are those methods that have the most overlapping features given this feature vector of the query code snippet. And it turns out that we can do this really, really fast. It takes less than a second for over 2 million methods. And so the output of this is, let's say, 50 to 100 methods that seem to be pretty close in terms of features to the code snippet that we started with. Okay, so we have now a candidate list and we still need to compute recommendations. So that leads us to clustering and intersecting. So what we want from clustering is that, because many of these methods will they could be different from one another, but some of these methods will be similar in the sense that they extend the query lines or the code snippet that we started with in kind of a similar way. So it makes sense to group those methods in the same cluster, and then we will have a bunch of clusters. The idea is eventually you want to get a representative recommendation from each cluster. So to carry all of this out, we designed a custom clustering algorithm. Again, we cannot really cover the details in this talk. You'll have to look at the paper, but let's look at it visually. So let's say we retrieved 5 methods that might have been similar to the query snippet that we started with. In these 5 methods, let's say those 2 yellow colored lines were our query snippets, and 3 of these methods extended the query in a certain way, and the last 2 of these extended the query in a certain other way. So you can now see where this is going. The first 3 go into one cluster and the last 2 go into another cluster. And then once you have done this clustering, then you can sort of compute the intersection of these to come up with a recommendation. So here we end up with 2 recommendations. So again, we glossed over a lot of detail, but this is roughly how it works. So this is how those pretty looking recommendations were computed by the tool and the recorded demo that I showed you before. Okay. Here is a, just showing, these are 2 methods from the same cluster. The lines highlighted in green were our query snippet, and the 2 lines shown in yellow are additional lines. And you can see why these would be in the same clusters, and you can also guess what would be the recommendation computed from these 2 methods that are in the same cluster. Okay, so now let's step back, and I want to make some remarks about the importance of this area. So I would say that now we have the scale of data that makes it possible, perhaps even inevitable, to leverage machine learning in developer infrastructure. So at this point, you should perhaps push back and say that, hey, we have been writing code for 70 years, all without ML help. What's new? We have done lots of innovations in compilers and languages and debuggers and testing and even processes like human code review and so on. So why do we really, need this, and why now? Okay, so I would say that so far, a lot of tools that we just mentioned on the previous page, the traditional tools, they don't really find particular use of certain kinds of information. So for example, if you have repetitive patterns in code, it's not really of interest to, say, a compiler, but with ML, you can harness that information for code completion, as we saw before. Or let's say you look at your version history and you see that, hey, a lot of times this same kind of small code change was made in commits. And yeah, okay, fine. But with ML, perhaps you can use the knowledge of those repetitive patterns for predicting bug fixes. Let's say, beyond symbol table, compilers don't really need names of identifiers, but you can use them for code search and so on. So there are many different things that come up as information that is generated in code, or when running code, or when revising code and so on, that we may not have previously thought of as particularly useful information, but with machine learning you can actually harness that information for some pretty interesting purposes. So, and then there is the point of why inevitable. So what has been shown is that many of these tools actually do impact developer productivity. And you can sort of relate to that intuitively, right? It saves developers the burden of routine tasks. It helps them find information they need. It helps to prioritize their attention, and so on and so forth. So I would say that the need for these kinds of tools always was there. It's just that we didn't have the scale of data and the ML know-how to really build models of these kinds. But now we do. Now we have that know-how. Having said that, it's not a fully solved problem. So there are lots of open questions, for example, beyond just finding new applications. So there is the question of how do you explain the predictions of these models to developers? How do you combine standard program analysis with neural techniques? How do you work around the need for supervised data sets? Those are sometimes hard to come by, and so on. And there are lots of pretty fun challenge problems in this area. So, for example, can you imagine an ML-based service that sort of acts like an automated Stack Overflow, where you write a coding question that you have in mind, and the machine learning system goes off and finds not only a useful code snippet, but also some explanation as to, that in the end helps answer that particular question, and so on. So these problems still need a lot of investment to create real impact. So finally, I want to leave you with some links. So these are various projects out there where there is sample code, there are data sets, there are perhaps papers, and so on. So if you look at these, you might find enough material to get started. So these are all pretty useful. And with that, let me end my talk here. Thank you very much.